Chemistry problem time. I'm really excited. We're going to start at number 1. Always a really good place to start. The specific heat of aluminum is 0.89 joules per gram degree Celsius. A relatively low specific heat, which we would expect for a metal like aluminum. It's going to heat up really quick, cool off really quick. How much energy is required to raise the temperature of a 15.0 gram aluminum can? 18 degrees Celsius. Wow, I'm really excited about this question. This is just a quick manipulation of our Q equals MC delta T, or MCAT equation. We're going to start by plugging in what we know. We're looking for the amount of energy, or Q, heat energy. The mass of our sample is 15.0 grams. Our specific heat is provided to us in the problem. How nice of them. 0.89 joules per gram degree Celsius. And we've got a temperature change here of 18 degrees Celsius. This one's pretty short and pretty sweet. We're just going to multiply these 3 values together. Our calculator is going to give us 240.3 joules. However, using significant figures, we've got 2 significant figures, so I'm going to round this to 240, no decimal point, joules of energy must be added in order to raise the temperature of that aluminum can 18 degrees Celsius. Wow. It's also positive. It's going to be absorbed by the can. Always a good idea, PS, on your free response to give your AP graders a really easy way to see what your final answer is. Don't make them hunt for it. It makes them really angry. So box it in. Let them know, hey, this is my final answer. Do you like it? I like it. Okay, let's move on. Question number 2 follows number 1. It says, if 596 joules of heat are added to 29.6 grams of water at 22.9 degrees Celsius in a coffee cup calorimeter, what would be the final temperature of the water? Oh my goodness, I'm going to have to use some algebra here. We're going to use the same equation, Q equals MCAT. Going to plug in our digits. We've got 596 joules of heat are added to 29.6 grams of water. Oh man, its specific heat is, luckily I'm a genius, 4.18 joules per gram degree Celsius. Our temperature change here, we want to know what the final temperature is, so T final, minus our initial temperature of 22.9 degrees Celsius. Can you solve this? First, let's multiply these 2 values together. When we do that, we will get a magical 123.728 grams times, well, actually the grams will cancel out. So we'll have joules per degree Celsius. I'm going to give myself a little reminder here, my little sig fig rule here. We've got 3 and 3, so I'm just going to remind myself, I should have 3 sig figs in this final answer. And that's going to be times T final minus 22.9 degrees Celsius. Okay, algebra time. We're multiplying these things together. Let's divide this by the 123.728 joules per degree Celsius. 123.728 joules Celsius. When we do that, we're going to wind up with 4.817. Again, a little reminder here, I should have 3 sig figs there, degrees Celsius. Equal to T final minus 22.9 degrees Celsius. See if we can finish this off. Well, we're subtracting over here, so let's add. We got T final equal to 27.7 degrees Celsius. My final answer. Woo. And again, we're adding. Side note, we're adding, so we're doing digits to the right of the decimal. I would have 2 digits to the right of the decimal here, 1 digit to the right of the decimal here, which is why I end up with 1 digit to the right of the decimal here for my final sig figs. I'm feeling so good right now. Let's just keep keep going. One more. Question number 3 of 3. If you take a look, it says a 5.037 gram piece of iron heated to 100 degrees Celsius is placed in a coffee cup calorimeter that initially contains 27.3 grams of water at 21.2 degrees Celsius. Wow, so many numbers right now. If the final temperature is 22.7 degrees Celsius, what is the specific heat capacity of the iron in joules per gram degree Celsius? Wow, I love this question. So good, so good. This is going to be one of those questions where the heat that's absorbed by one thing is going to be equal to the negative heat that's released by the other thing. Now, as we think about this, the temperature of the water goes from 21.2 degrees Celsius to 22.7, which means that it's got to have absorbed some heat, and that the iron in this example is going to have lost some heat. So I'm going to set it up, positive Q for my water, absorbing that heat, negative Q for my iron, releasing that heat. And then it's just a matter of recognizing what Q is equal to. Well, in each case, Q is equal to MC delta T. But again, I'm going to make this negative over here, just indicating that that heat has been released instead of absorbed. Then it's a matter of plugging in the numbers. We've got 27.3 grams of water times its specific heat, 4.18 joules per gram degree Celsius. Where did I get that number, you ask? Well, I'm a genius, so I just know it. And I encourage you to become a genius too. Commit that one to memory. You can't go wrong. As we take a look at this, the final temperature of the water, 22.7 minus 21.2 degrees Celsius is equal to negative the mass of the metal sample, 5.037 grams, times the specific heat of iron, oh my gosh, I don't know, X, times its temperature change, which will be final temperature when it reaches thermal equilibrium, 22.7 degrees Celsius, minus its initial temperature of 100 degrees Celsius. Okay. So now it's a matter of using our amazing algebra skills to solve this problem. If we multiply all of these numbers over here, we're going to end up with a positive 171.17 joules. Give myself a little reminder here in terms of significant figures. 3. We're going to subtract. There's some addition here, so we only have 2, because this is only going to be 1.5 degrees Celsius, so we'll only have 2 sig figs in this one, so we're just going to do boom. A little reminder there, we should have 2 sig figs in our final answer. So we do that over here. Mathematically, let's subtract these suckers, multiply it by 5.037. Keep in mind when you subtract these two, you're going to get a negative number. So this negative times this negative is going to give us a positive. So we're going to end up with 389.36 times X. Check that in your calculator if you don't believe me, but I'm really good. Slash I used a key. So 389.36, again, as we think about this, we're going to have no digits to the right of the decimal here because we've got no digits in this 100 degrees Celsius. So we're going to have 2 sig figs. We should have 2 sig figs, so boom, little reminder there. And then it's just a matter, let's do some division. 389.36. 389.36. X is equal to... Oh, this is grams degrees Celsius, by the way. Grams degrees Celsius. So when we divide that, we end up with 0.44 joules per gram degree Celsius, which is the specific heat of our iron. And that makes sense. It's a metal. It should have a fairly low specific heat, definitely less than specific heat of water. As you think about why, they're going to be absorbing and releasing the same amount of energy. However, notice our temperature change for the water is very low. Yet our temperature change for the metal is really high. And as you think about that, it's got to be related to the specific heat capacities of each of the individual things. Water's got a really high specific heat, so you put a lot of energy in there, but it's not going to cause a huge jump in temperature change. Conversely, though, your metal has a really low specific heat, so releases that same amount of energy, but boom, huge temperature drop. Really exciting stuff. If you have any questions about this, come see me at tutorials. It'll be a great time.